Okay, so let's talk about methods for correcting orthogonality error. And to get this started, let's look at where the orthogonality error actually comes from. So remember, we've defined the error as 1 minus the length of our quaternion, because the length of that quaternion should be 1, right? So 1 minus 1 will give us a measure of the error in the length of that quaternion. Okay, so here's our matrix that we're using to update the quaternion at each time step. So remember, the change in quaternion is dependent on the current quaternion and then our current rotation rates. Okay, so so this is one way to compute this, but let's look at this same the same development in a different form here. So actually, we can write E naught and E dot X naught, or E dot X, E dot Y, and E dot Z equal to 1/2 multiplied by so we can rearrange this and put P, Q, and R inside of this matrix here that we're going to develop, and then have the quaternion be this vector that we're multiplying by. And so anyway, I'm not working through the math, but because this is linear over here, because we just have a single component multiplied by a single component, we can actually come up with a matrix in terms of P, Q, and R multiplied by the quaternion. That gives us the exact same solution as this as what we have over here. Okay, so that's what I'm working through here. So we're going to have 0 minus P minus Q minus R, and then P 0 R minus Q, Q minus R 0 P, and R Q minus P 0. All of that multiplied by the current quaternion, which is E naught, EX, EY, and EZ. Okay, so these two are equivalent here. Those are equivalent. Okay, the mathematics works out to be the same thing here. Okay, so so in this form, we can see that we've got this diagonal of zeros here, and that diagonal, the zeros on that diagonal cause some mathematical issues. And so back in 1957, two authors, Corbett and Wright, this is in 1957, they came up with a method that can be used with direction cosines for minimizing the orthogonality error. Okay, so they actually applied it to direction cosines. But then in 1958, Robinson, showed that you could use this exact same method on this quaternion formulation. Okay, so we call it the Corbett-Wright method. But Robinson was the one that took the Corbett-Wright that was originally developed for direction cosines and applied it to quaternion. So same method. And basically what you do is you go through and replace all of this diagonal with a gain factor K, and then multiplied by epsilon. And that's that epsilon right there. Okay, so we're going to have K epsilon. That's an epsilon, K epsilon. So you put that on the diagonal, and then the K is a gain coefficient. So which is supposed to be just something large, and Phillips, again, I'll link Phillips's paper, Phillips, Haley, and Gebert, who go through this in more detail. But that gain coefficient actually is needs to be a function of omega. Omega is your P, Q, and R rates, right? So so right here, this is omega. So in order for this to be accurate, you have to choose a gain coefficient that's related to how quickly you're rotating, and then if you use this, then it turns out that it corrects for this orthogonality error, and it actually does a pretty good job for analog computations. No, so when this was developed back in the 50s, they were using analog computers. Analog computers are inherently first order. Okay, so analog computers are first order, and so their integration that they were using as they integrated forward in time was all first order integration. And when they applied this this Corbett-Wright method for getting rid of this orthogonality error, it would keep the error around 5%. Okay, at least that's what Phillips and Haley and Gebert show in their paper, that they could keep the error around 5% when they were using first order integration, which is very similar to the analog computers that were being run back there in the 1950s. Okay, so anyway, so this is a method. This Corbett-Wright method is something that has been around for quite some time, and you'll see it even in modern simulators. Modern simulators use this method to get rid of this orthogonality error. Now, what Phillips, Haley, and Gebert point out is that this is a fantastic method for first order integration, and that's the key here, because the computers back then were using first order integration. But today we don't use first order integration. We use second order or higher order, actually in most cases up to about fourth order integration. And so it turns out that this method is not very good once you, or is not very effective once you go to higher integration. And actually it can still be effective, but it's not very efficient. There are more efficient ways to handle this orthogonality error when you're using higher order integration. Okay, so so I'm just going to put a line here. So today we use higher order integration on digital computers. Okay, so they're not analog computers anymore. We can use higher order integration, and so usually that's between second and fourth order. Okay, and so there's another method that can be used to renormalize or to correct this orthogonality error, and that is simply to renormalize the quaternion periodically, okay, throughout the simulation. So the definition, or the way that we do that mathematically, is we say that the quaternion renormalized is equal to the current quaternion divided by the length of the quaternion. And you can write that out, obviously, so it'd be E divided by the square root of E0 squared plus EX squared plus EY squared plus EZ squared. Okay. So anyway, you can do this periodically throughout your simulation, and we're going to apply this every single time step. So within each time step, we're going to be using Runge-Kutta, fourth order Runge-Kutta, and so we'll be calling different functions 4 times. It does 4 computations within that Runge-Kutta routine. Once we finish with that complete time step, we'll come out of the Runge-Kutta routine. We'll use this this equation here to renormalize the quaternion to make sure that it still has a length of 1 before we continue with the integration. Okay, we'll do that every time step, but that's actually overkill. You really don't need to do it that much, but we're going to do that just to keep the errors small. But you can. It kind of depends. If you're rotating at really high rates, then you need to renormalize more often. But aircraft are usually not rotating at really high rates, and so you can get away with normalizing this quaternion a lot less throughout the simulation if you wanted to. You could do it every 10 or every 100 time steps or something like that, as long as the aircraft isn't significantly rotating or quickly rotating. But we're just going to do it every time step to keep the error small. Okay, so it turns out that if you use this method for renormalizing the quaternion, if you use that in a first order integration scheme, you actually get really poor results. You can have on the order of more like 9 or 10% error in your quaternion, or in this orthogonality error could be more like 9 or 10% instead of this 5%. So again, first order integration, this Corbett-Wright method is really good. And you'll see that today, even in higher order integrations, because it's like this legacy way of doing it. It's the traditional way. It's built into codes. People have been doing it for a long time. But this paper by Phillips, Haley, and Gebert show, and they do a whole bunch of computation here. They actually have an exact closed form solution that they developed from the quaternion for certain rotations, and then they compute. They repeat these computations and rotate an object by in the order of thousands of degrees, and then they look at the error, the orthogonality error in the quaternion, and they do it first using first order integration methods. They do it using higher order integration methods, and they are able to prove very convincingly that this method here, if you're using a higher order integration scheme, which is what we basically all are doing today in flight simulators, then this renormalizing the quaternion like this is much more efficient, and reduces the error just as effectively, if not more effectively, in most cases, than the Corbett-Wright method. Okay. And then the other thing that this is nice, if you just apply this at every time step, then you don't have to worry about this gain coefficient. That's a function of how quickly you're rotating. So this can kind of get messy, and the Corbett-Wright method is dependent on the gain coefficient that you're using, and obviously much more computation than this renormalizing here. Okay. So we'll be using this. One last thing that I just want to point out is that this type of error does not come from round-off error. There are two different kinds of error that we're familiar with. There's round-off and there's truncation. Okay, round-off error comes from the precision of your computer. So if it used to be that computers were single precision. Now today, pretty much every computer is doing things in double precision, and some of them can even do things in quad precision. So single precision, basically you're getting about 6 to 8 digits of accuracy in any number. With double precision, you can get up to 12 to 16 digits of accuracy. But they show in this paper that by Phillips, Haley, and Gebert, they show that even if you drop back to single precision, you get the same behavior and even the same order of magnitude of behavior. So this behavior, this orthogonality error, is really not too sensitive to the precision. Okay, so I'm just going to put a line through that. That's not what's causing this orthogonality error. The orthogonality error comes from truncation error, which is related to the fact that, so this is the fact that we have truncated higher order physics here. Okay, so this is, you can think of this as like we're using a Taylor series we're using a fourth order integration scheme, for example, to integrate forward in time. So we're only including certain orders of polynomials, so to speak, to represent the physics and things. So this is a truncation error problem. So this has to do with the order of the simulation. Okay, and that's where orthogonality error comes from. It's not a round-off problem, it's a truncation problem.